So we're streaming? We're emailed? Well, now's a good time since we are 10 seconds away from nominal start time.
I mean, we might be doing something nominal today. This has been a fairly successful meeting.
No major disasters, but the day is young. If you guys sit down and be quiet, we'll start the meeting. If you don't sit down and be quiet, we'll start the meeting and mock you. If I were to look at the schedule, it would say 1,300 hours. If we were going to start it at 1,400 hours, and today is it's 1,300 hours now, you know, we'd be starting it at about 100 hours, which is what, 3 days, 4 days? All right, be that way. So it is alleged that this is the March meeting of the Silicon Valley 4th Interest Group. So welcome to those of you that are here and those of you that are joining us on the internet, and those of you that will be viewing this video at some later time, unless we get a takedown order for something one of us says at some point in the near future. But we digress. So a couple of things are hanging fire that I'd like to wave a little bit about. And I'd like you to think about maybe if there are any rumors, gossip, announcements, things you want to say. One of the things I'd like to mention is that because of our very successful Maritime Flag Challenge on the 4th Haiku site, we're motivated to maybe think of another challenge and publish it on comp.lang.4th. But maybe we'll challenge people to come up with an interesting challenge and post that to comp.lang.4th. One thing I wanted to mention, today is Arduino Day. So I guess if you go to SparkFun and their website, they may give you a better price or something. All right. Dennis is sort of nodding, I guess. All right. The Embedded Systems Conference is coming up sometime soon, so those of you like me who have to announce your vacation time well in advance might want to peruse the impending keynote speech and decide whether you want to be there. It seems like now I go to these things pretty much out of habit. John? Yeah, Maker Faire, that's a good thing to... I did want to mention that in May, there is a date in May for a SVFig meeting, 16th and 17th? There's a date for a SVFig meeting in May, but it has been my custom to go on vacation in May, so I won't be programming that meeting. It is traditional that we have just skipped the May meeting in favor of Maker Faire, so that is my official position. That's my story, and I'm sticking to it. All right, so we got the Maker Faire, we got the Embedded Systems Conference, and we talked about an Arduino Day. And does anyone else have rumors, gossip, announcements, comments, slander, libel? Anybody want to stand up and explain the difference? You'll just stand next to me and I'll not touch the microphone.
Speaking to your sternum. couple giveaways. This is a bus board.
What kind of bus board?
64 character bus board. 64 pin bus board. I'm not sure what it would go for.
Step back 2 steps to make the camera work easier here.
So this is up for grabs for free. Okay. Also have a much more valuable Ampro single board computer card. And it looks like it needs a BIOS chip here. And so somebody gave these parts to me. So I'm offering them to you guys. So please let me know if you want this. Thanks. Free.
All right, comments, announcements. All right, so without further ado, we're going to take a 2-minute break to give John a chance to accustom himself to the changed circumstances, and then we'll continue on.
Okay. Can we hear me? Hello? 1, 2, 3, 4.
Put it on talk. Is that right?
Yes, talk is the place that
Talk
it's
is
on
good.
talk. And it's on the guy that's taken over the late show says something.
That's it.
Go for it. It gets a laugh at least. It's not stress. Find that and use it. We're running out of water. Thanks.
Oh,
We're on a. Got to
Yeah.
keep moving.
Is there a setting you can turn off your timer? So
I'm going to keep typing.
you say that now. Can we mock
you the details.
Okay. All right. So I've been working on fourth drivers for the FT800, and the FT800 is an embedded GPU. It's kind of a new thing. It's like an LCD driver, but most LCD drivers just give you a frame buffer, and then you have to write software rendering code to draw a bunch of pixels. But the FT800 is a lot more like a real GPU. You send it drawing commands, and it draws the stuff on the LCD. So it sits between the LCD and the microcontroller. And the microcontroller, I'll show you how it works. It's simple enough. You just send commands over this two-wire interface, SPI. So the way I've got it set up here, I've got some code here on my laptop, and I've got a video on my laptop of the demonstration. But I also have the real thing here running on a battery, which is an FT800 with an LCD and a microcontroller, running the same demo, which I will pass around the room. So it's running exactly the same code. So as I run through, you can hold it in your hand and run it live.
So how do you get back to the...
So you put three separate fingers on the screen, and that's the Control-Alt-Del to reboot.
Intuitively obvious.
Yes. Okay. So it's all in GitHub, and here I've got a copy of the tree on my laptop here. So I'll start off with the first of the demos, which is Hello World. So there's a library called GD. This is originally to drive this thing I made, this project for Arduino called the GameDuino. GameDuino is just really an FT800 and a screen and a few other odds and ends. But really, the core of this is a driver for the FT800. So the GD is a bit of a leftover artifact. So when you start, you call this initialization function. Here we set the clear color to be this hex number here, which is a beautiful shade of green. We issue the clear command, and then this line is drawing some text. It takes a bunch of arguments. We've got an X coordinate, a Y coordinate, a font. This means draw it in the center of the screen, and then a regular fourth string. And then finally, there's the API call to actually draw a string on the screen. And the FT800 works a lot like OpenGL. You call swap at the end of your drawing commands, and that's what makes it visible. So you don't get any flicker. You draw all this, you begin drawing, you clear the screen, you draw everything on the screen, call swap, and then it flashes onto the screen. Exactly. So it's a double buffer. So you're building up one buffer while the other one's being shown on screen. So things only flicker if you do it on purpose. And you're asking, what does this look like? Well, here's the video I made earlier. There we go. Hello world. So it doesn't do a whole lot, of course, because it's drawing the same thing every frame. Every time through that infinite loop, it's clearing the screen, drawing the text in the middle of the screen, and then swapping to make the new one visible. But this is happening 60 times a second. It's just that it's completely static. So that's the basic way that the GPU works. When you issue each of these commands, what's actually happening is that it's being serialized over the SPI bus to the GPU. So what the fourth driver does is it takes its arguments. For example, here's GD command text. It takes its 5 arguments, turns them into a stream of bytes, it serializes them, and then sends them over to the GPU. So there's actually not a whole lot of graphics. Oh, you found Frogger. Great. And there's not a whole lot of graphics going on the fourth side. All the driver does is serialize. It does a little bit of housekeeping as well, but things like the text drawing is handled on the GPU. GPU's got a bunch of features. Some of the drawing commands are kind of low level, like clearing the screen, and some are kind of fancy, like drawing text. And there's a few other even fancier ones I'll get onto in a minute. So say you have a pressing need to display a number on the screen. Here's a lot like Hello World, except it's running in a very long do loop. Same stuff to clear the screen to green. This again is the middle of the screen. Font number 31, centered, but this time instead of drawing text, instead of doing command text, we're in command number, and the number we're going to be drawing is I, the loop counter. Well, oops. So these are actually digital captures I'm showing for some of these. All right, so here's launching count, and there we go. It's counting at about 60 hertz. So it's every 60th of a second, the swap happens. We get a nice smooth counter running full speed. Okay, so that's me, my video of that same unit. Okay, what is next? Fizz. Okay, so these are all conversions of original demos from the Arduino version. So a lot of these are converted from the C, for better or worse. So everything here is ANSFORTH compliant, except for a few extensions. Obviously, we need the GD library to actually drive the thing and run the graphics. The other thing I need is random numbers, which obviously aren't part of the ANS standard. So I've just defined them as an external call here. So what does this function do? It initializes, it grabs the width and height of the screen, gets them on the stack, and then it starts drawing points. So points in the FT800's API are a lot like OpenGL points. They're actually circles. And if you draw a point which is 1 pixel in radius, it looks like a dot. And if you set the radius to something enormous, then it actually is revealed to be a smooth anti-alias circle. So though they're called points, they're really circles. We choose a random number. RR is the random number generator, and set the point size. We choose an RGB triple. 256RR generates a number in the range 0 to 255. And we do that 3 times to generate an RGB color. We set the alpha, that's what GD color A does, which sets the transparency. So we've randomized the point size, randomized an RGB color, and randomized the transparency. And then draw a random point on the screen. That's what we've got. That's why we've got width and height on the stack, so we can do over and generate a random XY coordinate. I call GD vertex 2F, which is just like GL vertex 2F in OpenGL. And this is all inside a 200 loop. So just to be clear, every frame it clears the screen, draws 200 points, and then does a swap. So here's it live, clicking on Fizz. So it's a bit of a problem for video encoders, because this is actually running on the real hardware. If you're the one holding the machine right now and you're running Fizz, you can see it actually looks a lot better because it's running at 60 hertz. But obviously when you run a video, what you really don't want to do is have random stuff changing every frame. That encodes really badly. So it didn't do a great job. Yeah, the real thing. Looks a lot better in real life. Okay. So that's Fizz. So a lot of people do that with their embedded graphic system. They just draw things on the screen as fast as possible, and you see a whole bunch of circles or rectangles happening on the screen. But it's important to see that the difference between this and software rendering systems is that they generally have a single frame buffer that they draw into on the screen. And you can see the circles or rectangles being drawn on the screen because they're just drawing them as fast as possible. This is drawing a different 200 every 60th of a second because it's a genuine GPU. You've got this hundreds of thousands of primitives it can draw per second. So double buffer rendering is obviously just out of reach of software rendering systems like that. Okay, so this whole GPU is really aimed at making embedded control systems. So buttons, dials, gauges, for people who want to build embedded devices and make a user interface for them. So it's not really made for graphics in general. It's targeted at controls. And what they have is a whole bunch of built-in widgets. So we just go back to that and just pause that for a moment. So this has a whole bunch of widgets on it. This one here is a rotary gauge for like choosing an angle. These are a couple of sliders. This actually says this and that. It's a two-way picker that lets you slide a button just like on a phone or something. These are buttons to click. That's an analog clock. This is a gauge which is used just for indicating a single value, but it draws a sort of analog gauge type thing. There's a keyboard down here, obviously, and this is a slider, a scroll bar. And then this is just the number. And this whole program, all of these controls are all hooked up to the same single variable in the code. And each of them is just a single API call to draw something on the screen. You have to tell it its coordinates, and then it draws everything for you. So it's one call to create an analog clock into the hardware. And so the fourth interface is just providing an API for each of these things. This val here, ingeniously named, is the value that you're actually manipulating, that all the widgets are controlling. And then going through the code, you'll see something. If I look for clock, there's the coordinates and the options to draw the analog clock. And next to it, there's the same thing to draw the gauge. All of these things are one call in the code, and then there's a little bit of extra stuff to run the interactive widgets to allow you to change the values. So here's me messing around with it. So there's the rotary thing. As I wind that, it's changing this scalar value. And here it's running in autopilot mode. Right? You can see that they're all linked together. This all just happens because they're all being drawn at 60 hertz.
So I think you just answered my question. This is all immediate mode graphical interfaces, not mechanical.
Yeah, right. So nothing is sitting on the G. So even because all you're sending is a few characters over the SPI to make everything happen, even something tiny like an Arduino can easily draw all this at 60 hertz. There's maybe there's 500 bytes to draw everything. So relatively, even something really lousy like an 8051 can still do an interface like this. It's immediate mode. So everything has to get drawn every. And actually, on the mailing list I run for the FT800, a lot of people say, well, there's some way to keep things on the screen. You have to say, well, no, it's a GPU. You have to clear the screen and draw everything every time. But so nothing ever gets retained. So one options on all the widgets, they have a 2D look and a 3D look. So if you switch on 3D, you get this sort of shadow effect. And there's the 2D, which is a bit flatter, a bit plainer. They run a little keyboard, and this is it's actually one API call for each horizontal row of keys. And here I've hooked up a little bit of code so you can type stuff in. So the FT800 is obviously a GPU with all of these drawing commands, but also runs the touch screen. So that's got a capacitive touch screen on the front, and it reports the XY touch coordinates back to you, and also tells you which object on the screen was being touched. So you can build a loop, which here. So this is actually the section of the code which is drawing the keyboard. Sure, Brad.
So the text that's being retained there, is that going across the gap 6 times a second?
Yeah, so if we look at something like so this is the actual implementation of something like command number, which is the thing I showed earlier, which plots a single number on the screen. And if you look in their data sheet, they say it's command to, you send a byte to E down the line. And then these are the actual options which are on the stack, right? And this N is a 32-bit number, but all the others in the data sheet it lists as 16-bit numbers. So the way I implemented it is I push N on the stack because it's going to go out last. And then HHHH takes 4 things on the stack, 4 half words, and serializes them out over the bus. And then I pull N back, and then I send that over the bus as a final 32-bit. And that's all there is to it. It's just serializing this stuff out. And so all of these things are all just mechanically converted. I've got this giant one to send 8 things over the bus here. So all that happens here is that these get serialized. And if there's a string, it gets sent out with a null on the end. So the GPU is just listening on the end of this link. Right, so it sends a little string out and it draws the keys in a keyboard configuration. And that's the entirety of the keyboard code. Keep it going, please. Everybody's had a look. Okay. When a key gets pressed, you can actually just read a register, and it tells you which button got pressed on the keyboard, which is a lot easier than looking at XY coordinates on the screen and trying to do a collision detection, trying to find out what got touched. Okay. Oh, good. All right. So, speaking of touch, here's one of the early demos that I made for the Arduino. Right. So this is taking the XY touch, and it's just drawing a circle, and it keeps track of the last 128 circles, and it expands them as they age, and decreases their transparency. So, whoops. Right, so they actually become transparent as they go through. So the GPU, everything to do with drawing is completely free, which is different from software rendering, where everything costs. If you want to do something fancy, it costs a little bit of CPU power and slows down. With this, it can do transparent circles, no problem at all. So everything's still happening at 60 hertz. The code to do this, these are all part in the demos directory. Right, so I keep an array of blobs, circles. These are just coordinates. And to begin with, I set them all to off-screen. I sense the inputs, and if there is an input, then I load up that circle into the next blob element, and this is where it gets written. And then there's just another loop down here to render them all, and choose a random color for each one, and sets the point size according to their age. So that's all there is to it. It's actually about the same size as the C version. It's kind of interesting taking a bunch of C code and converting it to 4. It didn't actually get much shorter. So it's, but that is blobs. And this next demo is, I have to wait for blobs to finish. So a lot of these demos just use core forth and integer math. This next one, I wanted to do something simple involving floating point, because I've just got floating point working with my actual forth. So this one's doing trig, sine and cosine to compute the vertices, and it's just using simple line drawing on the GPU. So it's actually the same function drawing each of these circles. Okay, so it really is floating point math, and here's the function which draws a wheel. It just runs around the outer edge of the wheel, computing the sine, using sine and cosine to get the x, y coordinates. And it uses a little bit of modulo arithmetic to step around the perimeter to get that spoke effect. And I think, right, and those are it sets the color for each of the four different wheels, and then draws them with a different radius. And that's it. So it's using floating point. I wasn't quite sure, because I just implemented sine and cosine. I actually wanted to check out that they produce reasonable values. So there we go. Test passed. That is the pinwheel. So the hardware does anti-alias line drawing. Didn't see any jaggies there because it's smoothing them. This next demo is high-speed animation. So it's drawing a bunch of anti-alias points. And this one isn't using floating point, but is using an object library, which comes with G-Forth, and it's like this one block of code, mini OOF. It's okay. I've been using it for a while now, and right. So mini OOF is the thing. Does the job. You have methods. So each dot on the screen is an object, which I've once again called a blob. So I made a method to place it randomly and a method to draw it. And each of them has an XY position and an XY velocity. And there's various, and then I just filled in the methods to draw them and to animate them. So mini OOF on my embedded CPU is about 700 bytes, which is good value for money. I mean, you get an object-oriented programming system for this minuscule amount of code. Okay, so there's various stuff here to do the drawing. Okay, so.
Those balls, the blocks.
Yeah.
Do they interact with each other?
No, it kind of looks like they are, but in fact they're completely independent.
Okay, they basically bounce off the boundaries.
Yeah, they're just following their own trajectories. I mean, if they interact, you'd have to do some sort of n squared, and it would get really expensive. So it's a sort of cheap hack.
So it is like the ideal gas law.
Right. As if collisions never happened. Yeah. Right. Yeah, it's yeah. As soon as you get into that whole collision thing, you're in this sort of n squared computational expense. That's a big computer thing. This is a small computer thing.
Can you read the pixels off of the FT800?
Kind of, but slowly.
Oh, okay.
Oh, you're going through SPI, right?
Well, yeah, you also have to wait for it to render the frame. You can ask it what's on any given pixel at the end of the 60 hertz interval. So that's how the touch system works. It tells you what the touch pixel was, but only after the end of the frame.
Because a poor man's way of binning things would be that if you, okay, these are little tricks, but if you have two things that overlap,
Yeah.
then the thing would be darker, or it wouldn't be a pure color, and you could do image detection from a pixel if you're willing to have one pixel overlap and then respond with your code.
Right. Yeah, you can do that easily enough when you're doing a software, when you're actually touching the pixels. With this, the pixels are kind of out of your hand, so you don't even get told about.
Yeah, but like say with the HTML canvas, you can do all sorts of tricks to Filter the canvas quickly and then detect where things hit by accident.
Oh, I see. Looking afterwards, yeah.
Okay.
Right. Yeah, you do get to, there is a thing where you can actually ask one pixel on the screen, you can say what was on this pixel. And you get to, and I'll be demonstrating that in a later demo, but that's all you get. So I don't think it's really made for doing anything other than user interfaces. Okay, so this one is, there's a lot of things. So when it says loading, it's actually loading the map of the world as a JPEG from micro SD card. One of the API calls that the GPU offers is load JPEG. So you just say, I've got a JPEG here, load it into memory for me, and then you just pass the JPEG over the SPI. So that's how it's loading the image. The fourth driver doesn't know anything about JPEGs. All it knows is how to pull it off out of a file and then push it out over the interface. And that's how the map of the world gets on the screen. So that's the first thing. The next thing is, I'll just let it, there we go. The next thing is I'm using Neil Board's calendar code. He's got a bunch of calendar manipulations, and they actually let you work in Julian dates and then display and do the calendar calculation. So that was the first component. So Neil's stuff's great. It all seems to work great with ANS, with 32-bit ANS forth. The next thing is I took the equation to figure out where the sun is, its latitude and longitude of the sun's point for any given Julian date, and then turn that into rendering the sun's position on top of the JPEG. So as you can see, we're going forwards in time, like 1 day every frame, and you can sort of see it going, lighting up the northern and southern hemispheres as we go through the year. The last part is actually doing the lighting. So obviously the sun is being placed on the map of the world, but what's drawing this nice curve around the outside is actually doing the math to illuminate the sphere based on the sun's position. So that's a whole bunch of lighting calculations, which is happening on the CPU. That's a fourth function to compute this light map, which it then transmits over the SPI and then does another drawing command to draw the light map on top of the map of the world. So, and then finally it actually draws the sun on top as a last layer. And a little bit of text at the bottom to show the current date. So there we go. It all seemed to work fine. It was an interesting difficulty because my floating point system on this fourth I'm using is single precision. Single precision floating point for representing a time is kind of problematic if, as time progresses and you represent it in floating point, because floating point has a fixed number of significant digits, it gets more inaccurate as time passes. Close to 0, you've got lots of precision for your time. And when you have a large number, say you're at day number 5,000, as we are now, because we're 5,000 days after the year 2000, the 5,000 takes up about 12 bits, leaving only another 12 or so bits in the mantissa of a single precision floating point for the time of day. Well, that's actually about 1 second. So your time stops representing, hopefully, milliseconds or anything and starts increasing in 1 second ticks if you take your time as a floating point number. And you could imagine somebody using floats for time and then time getting grainier and grainier as the decades pass until finally you're doing 1 year per tick. So obviously I had to switch to fixed point for doing all of the time calculations.
Well, the next time is a 64-bit integer.
Yeah, floating point is bad for, yeah, bad for almost everything. You have all your precision down and next to 0.
I've always asserted that it was the work of the devil, which is why the old floating point coprocessors ran so hot.
Evil. So that was the thing. So yeah, that had to happen. So all of the angle calculations happen in fixed point, and then as soon as they're in the range 0 to pi, that's the time to switch to floating point. That works fine. So it all hangs together. Yeah, there's no visible bugs, and as far as I can tell, it's doing the right illumination calculation.
The image, you're sending that across once, I assume. But you're not sending the image across each frame, right? The image is retained.
Yeah, the image, so there's two layers. Well, there's the sun, obviously, which is just a circle. There's the map of the world, which is a fixed JPEG, which is almost all of the frame, and then the next layer is a light map on top, and that's a monochrome image, which then gets to illuminate the background image, and I'm sending that across every frame.
James, I noticed that near dusk or dawn,
Yeah.
at least you have, it's not a sharp boundary.
Right.
See, there's like a shading.
Yeah, yeah.
You were able to accomplish that?
Yeah, so when I do the lighting calculation to figure that out, right, you've got the, so it's drawn as a rectangle here, but think of it as the original sphere, then every point has a normal,
Right.
and then there's the sun angle, and then when the sun is at 90 degrees, you're getting no light,
Right.
and if it's at 0 degrees, you're getting full light. So
Okay.
it's actually doing a cosine for every
Right, but
pixel.
This, not this, not the sun, not the map.
Right.
It's like a transparency value you're using.
Right, so I've got the illumination map, and it's just using a byte per pixel. So these are all zeros up here, right? And these are all 255s in the fully lit region. And in the place where the normal is in between those values, then you get the partial illumination. And
Illumination, or in this case, less transmittivity. It's not as transparent.
right, and then the net effect is after it's been fully rendered, it's just dark and light
Right,
again. Right.
You're not illuminating. You're just making the background less transparent as you get towards darkness.
You're right, because what I'm actually doing is I'm actually I draw the map on the screen, and then just to save a little bit of fuss, I actually just set the color to black, and I'm drawing the shadow. So I don't draw the light, I draw black. It's actually being rendered as a black shadow on top.
So are you drawing a whole bunch of pixels, or are you actually drawing a region and then doing a fade? Because you're having to send a lot of pixel information of the shading or transition.
Well, there's another trick I'm doing. So this is a real GPU. So what I'm really, think of it more like uploading a texture into a GPU.
Right.
So I'm not actually sending I'm sending it a texture, and then I can do some drawing commands that use that texture. Because this whole region this is actually, it doesn't look like much, but it's actually like 500,000 pixels or something. I really don't want to be sending that. So what I do is I take that texture, and I'm using a low res version, because there's no real detail in the shadow map. So I'm actually shrinking it by a factor of 4, I think, which obviously makes it a lot smaller. So I'm not sending 1,000,000 pixels every frame. I'm sending 1/16 of that. And then I send the drawing commands to scale it up when I'm doing the drawing stage. So if I had a sharp boundary, you'd be able to see these great big chunky blobby 4x4 pixels as my illumination map. But because it's a soft shadow, you kind of can't see. The other thing is that the GPU does bilinear filtering, which smooths out that chunkiness, right? So there's quite a lot of GPU style tricks going on here. So it's a combination of a little bit of lighting rendering happening on the CPU, and then the GPU does all of the final blend.
So you could theoretically get some of that shading by having a black and white transition and running GPU filters to smear it.
Oh yeah, yeah, could do. Yeah, I mean,
It may not be as accurate, but it'd be close.
right. Yeah. But the thing about when you see this thing running is that it's kind of complicated, the pattern of lighting that you get. So it's the math of computing the spherical lighting, right? So for example, that's the moment of, or pretty close. That's the moment of equinox, everybody in the world is getting 12 hours a day and 12 hours of night. And then a moment later, like back into, I think that's winter, Northern Hemisphere winter, right? So when it zips along like this, it's fine, and you could probably use an approximation. But really, when I've got it running just as a regular clock, it's sitting there. You kind of want your local sunset to be exactly right. So I don't really want to use an approximation. It's certainly true that there are only 365 interesting configurations. So in fact, you could just keep them on disk. Okay. So that was a lot of fun, and it was nice to use Neil's stuff, of course, and to debug all of that. And that's the fourth original. This last one is a conversion of a C sample that I wrote a few years ago, actually. Terrible 8-bit video game, and you can get all the graphics off the web. People have taken the arcade machine and extracted all the pixels. So this is all self-contained. Here's me trying to play it. I'm terrible at this game. Oh, there we go. Here's one I prepared earlier where I win. Oh, all right. So this whole thing is about 400 lines of forth. And it's not using any of the fancy drawing commands, because everything is just drawn using a bitmap. So it loads this. In fact, all of the game is just one texture. You just load this rectangle, which is just a single page with everything in it, and then it's effectively drawing tiny rectangles for all of the sprites on the screen. Every frame to draw the background and the foreground. I think that's all I've got to say about Frogger. Oh, there's one other thing. This is actually the collision detection in Frogger. How do you know when he's been run over by a car? This is actually using that single pixel readback. So it sets a single pixel on the tip here, and then it queries it at the end of the frame to see if it's been touched by a car. And then a bit of game logic decides what to do. If you get touched by an object in this layer, it means you've been run over and you're dead. When you've got to the river stage, it's the other way around. If you're touching an object, you're sitting on a log and you're alive. So that's using this single pixel query to find out what it is that the frog is sitting on.
So when you're in the bottom half, if you're getting run over by the car, you're going to get hit on the right side of the frog. So you'd be looking at the right pixel of frog. You go to the next row, it's the left side. I
just use the center pixel. It doesn't seem to make, things are moving so fast, it doesn't seem to matter. People seem, particularly if they get away with not being hit by something, then they, oh, seems fine. They're very sensitive to oversensitivity. When something comes near you and kills you, people get very cross about that. But,
I want my quarterback.
So I really, this is the first time I've actually tried to deliver some public forth code, and one of the things that I really wanted to do was make it work with other people's forths. This is, if you like, a next layer up. This is using a forth. I was using this to debug and develop my own forth, but I wanted to give it to other people so that other people could take their forth and then drive this GPU with their other forth. And McCrisp forth, which is runs on various things, I sent him the code and he got it running. So it was very satisfying when he sent me his screenshots of his demos all executing this forth on his ARM CPU. So this forth driver running on his ARM forth. How do you know that your forth code is properly ANS compliant? How do you know that you haven't used some word which isn't part of ANS forth? So a few years ago, I took another thing that Neil had made where he wraps up all of the forth words inside aliases, and then uses a vocabulary so it restricts the forth words to just the ANS words. So here's the sort of thing I'm talking about. You take every word in forth, and there's a bunch of other stuff going on here, but there's the general idea that you're working through all of forth, and you wrap it up in another vocabulary, right? So, for example, cell plus is an alias for cell plus. Some other things going on there, but what you end up with is a forth which just contains the new things in this vocabulary. So I take G forth, which has a bunch of extra words. For example, it's got words like greater than or equal to, which is not part of standard forth. If you test your program by running it on G forth, and you use greater than or equal to, like many allegedly standard ANS forth programs do, compiles fine, you'd be none the wiser, and you think you've written an ANS forth program, but it isn't an ANS forth program. But this, there is no greater than or equal to. So if we type words here, we get the original forth, ANS forth words. We don't get the words which were part of, which have been added by Gforth. And it wraps up any forth. It works any forth that is ANS. It wraps it up, and then you end up with this pure forth. That was the thing that Neil did, and I took it a few years ago, and it's quite nice. You can run your code through this forth inside a forth, and you're running in a restricted environment with just the pure words inside it. So I could be reasonably sure that I hadn't used some illegal word.
Or something that's specific like to a particular form.
Right. I mean, I could still be relying on things, properties of the forth, of like making assumptions about words, for example, that maybe differ between forths. But at least then I'm not using some part of the vocabulary that isn't standardized.
Right.
But taking this one step further, I actually wanted to generate the labels for the program. If go back to the demos, you'll see that each of them has the forth label, which says which parts of the ANT standard it's using. So what I did was I added a little bit of flags work inside each of these words as they get used to set a flag to say which part of the forth standard got used. And then I've wrapped it up by, so that if at exit, it prints out a label saying what got used. So if I do, won't do plus, say 1, 2 plus dot. So I've used some of the core words, and I think if I say by now, yes. So I typed in by, and it's done that. So it's told me that I used the programming tools word set, and because I use actually dot is part of cores. Yeah, you're right. Words. Right. So you've got to be careful because there's this sort of contamination problem. So if I do a little bit of floating point here, ta-da! It's magically detected use of the floating point word set. So I can actually run all of these through when just at compile time. But if you compile it and then type by, you get the label out of it. So let's see, did I label this one? Yes. So this is actually the label generated by that program. So it compiled it, checked that it's ANS compliant, and generated the proper label. Say, if you built your forth and you grab this, you can tell ahead of time which parts of forth you need to have implemented in order to run this thing. Some of the demos just use core, but this one does something which uses facility. I can't remember what. And that is how, so far, I've got checking that it's a proper ANS program. It's sort of an automatic system. So you can actually just run the unit tests, and it checks that it's a valid ANS program. There's a few other things it could do. I mean, this is a bit like valgrind for forth, right? With valgrind, you're running your C program inside this virtual environment, which does extra checking to make sure it's legal. Be quite easy to overload, for example, variable and value to check for uninitialized, to check for read without write, for example, or other illegal activities, and go further down that route of automatic checking of your forth program. You just run the code, and just like Valgrind, you get a report at the end telling you what it's done wrong. That's all I had. Thanks a lot.
In dollars and cents, why are people interested in FT800s? Cell phones now have become such a commodity thing that a screen with touch and a CPU underneath it. That's the $50 region for hardware people.
Oh yeah, but this chip is I don't know, $3. So
Okay,
so the LCDs are like very cheap,
okay,
particularly in volume. I mean, they're
yeah.
so something like this one. I've never actually bought one directly in those sort of 1,000 unit volume, but they're about $3. So at the sort of $6 cost, then you
That
get a screen.
explains everything.
Right. So for things like appliances, for a washing machine or a microwave oven, you don't want to put a cell phone in there. You want every cent counts.
I see model railroaders who have a dozen iPads around that control switches on their model railroad just because it's the easy way of
I
doing
see.
things. So it's what saves them money.
Yeah, but they'll buy something, they'll,
And for the folks online, I avoid us getting a takedown. I will play a small video in the midst of the presentation, and like last time, I'll turn off the audio during so we don't get sad. Not sure it's quite as topical as the last one, but anyways. All right, we're all set. Block editor 2, blocks of doom. Okay, so the motivation, simple. I use a text editor every day. I bet each and every one of you use a text editor every day. Go around the room, each of you. What's the editor you use every day, Kevin? To edit documents. What do you edit documents with? What do you?
Email.
Notepad, Emacs, okay.
plus plus.
Notepad plus plus.
HTML text area.
HTML text area. Them, all right. What he said, yeah, me too. Woo. All right, cool. So we all use text editors. I mean, we're people, we're programmers. We edit words for a living. But Forth has this legacy of a very powerful but very small editors, and that's not the editor I use. I use Vim, which is, it used to be small and minimal, and now is big and huge and complicated. But the trouble with these Forth editors is, well, they're weird and they're incompatible with things, and they don't have some of the things that I want when I use a text editor. So, can I add the features I want to one of these block editors? Can I make them something I could actually use every day, but keep them from turning back into a big complicated thing that I'm trying to get away from? So what I want to do is I want all the cool features, but I want to learn from history. So I'm going to throw in the video here because it's topical. And so I want to, I want to be the man that handles the blocks. So we'll see how appropriate this is, but anyway.
I am the man who arranges the blocks that descend upon me from up above. They come down and I spin them around till they hit in the ground like hand in glove. Sometimes it seems that the blocks is fine and the lines will be formed as they form. Then I see that I have misjudged.
So I'm not talking those kinds of blocks, I'm talking forth blocks. 1 kilobyte blocks on disk. Really what this is it's virtual memory for forth. And it's got a great dead simple API. You want block number 3, you say 3 block, and you get back the address of a 1K block. If you've changed it, you need to call update. If you want to flush things to disk, you call flush. It's marvelous, simple, and beautiful. You can use it for data, but you can use it for source code. And this is the genesis of all sorts of fun things with editors. So using blocks for source code, the traditional convention is a 64 by 16 block of source code, and by that I mean a grid. No carriage returns or flow control here. This is just a grid of characters. There's simple standard words to load from a block. You want to load block 3, you say 3 load, or you can load a range of blocks. So this gets to block editors 0, the origin story. Your classic prompt block editor, which basically is a line editor with some 1- and 2-letter commands for changing particular lines. They're really, really small. They're very small, a few blocks. The editor of this sort that comes with gforth blocked has 1 block of docs and 3 blocks of code. But that's not the smallest one I've seen. The smallest one I've seen is in RetroForth. They have a 1 block editor. It's a marvel of compactness and simplicity. All you need to edit your source code in 1K. And the idea is just, you display the block, and there's a set of small commands to edit them, typically line at a time. What more could you want, right? But that brings us to block editors 1, the motion picture. So these are what I'll call the screen editors. And this takes the idea of a block editor, but sort of takes it 1 step further and makes it something you might actually want to use day to day. And these editors often have, also a very small source space, maybe a dozen blocks. My favorite is the old PygMyForth block editor. It's marvelously integrated into the system. But another one I came across recently is Vibe from our own Sam Fallow. In fact, I actually encountered Vibe not realizing it was Sam's. Realized, wait a minute, aha. And they're great. And there's a number of reasons. But talk about variations first. Shadow blocks. So almost all of these editors use the notion of shadow blocks. I'm not personally fond of shadow blocks. I know that seems to be a minority opinion, but the notion is that you keep a pair of blocks together, 1 for source, 1 for documentation, and they're sort of chained at the hilt, chained at the legs, and you can toggle with 1 button back and forth between them. I find that this separates the code and the documentation in my experience, but others seem to have fun experience. Some folks, particularly the PygMyForth editor, play games with mapping different regions of the block number space to different files. ColorForth even manages to use blocks, and in all the ways that ColorForth isn't standard, it at least uses 1K blocks. They're displayed completely differently. You just have freeform source where the particular words involved affect how it's displayed. So what are the good things here? What do I want to keep in my block editor? I want to be able to focus on small pages of code. What I love about a block editor is the constraint, the idea that you've got a fixed size canvas, a small space to make your 1 piece of module, your 1 thing in. And I also like that they're tiny and powerful. They do a lot with a little bit of code. And something else that I really like is that they really get you thinking about 2-dimensional space. Very often when you have programs that are specified in a text file, you've got these carriage returns, and the carriage returns are not they're not a natural thing. They're an artifact of the encoding you've used on disk. You as a human being see code up on a screen on a 2D grid, and the carriage returns are just an artifact of how it's presented. So you find yourself in the editor, dodging your way around the carriage returns, or worrying about things like trailing white space, and you end up having conventions about what should be on disk turn into where I work. There's a style convention of no trailing white space, and it's, you know, it's not a big deal. You can set up your editor to strip it off, but it's reflected in how you navigate the thing, how it appears on disk. And I find that in a block editor that doesn't obligate you to think about this, that you more often think about, well, would this be better presented side by side? Would this be better presented flush to the right, flush to the left? You do a lot of things in terms of formatting that you wouldn't otherwise consider to more visually present the ideas you're trying to convey. And I just generally like them because it's a constraint that I think leads to art. It's you know, a fixed size space means that you have to really think about how you're going to fit what code you're going to put into it. And they're fast. They're you know, small programs. They start up. They have a very simple encoding, and there's not a lot of configuration files to load or anything like that. It's not Emacs sitting there spinning up, chewing on a ton of eLisp to get the world going. But there are some bad things. That 64 by 16 is awfully tight. It's smaller than modern source code. I mean, you know, the bare minimum code I come across is 80 columns, at least day to day. And but even for Forth, even for sort of the perfect case for it, I find that 64 by 16 is a little tight. Now, it's probably a little tight in a good way. It's a little tight in the sense that it's sort of, you know, you feel that boundary and you're taking it into account as opposed to just blathering on. But nonetheless. And then, of course, there's all the poor interoperability with the OS. Your C compiler is not expecting to load 1K blocks as its input. And there really are none of the modern conveniences. You know, you're not going to see syntax highlighting. You're not going to see folds or any of this sort of stuff happening in a block editor. And something I found with a number of them, at least the ones I've written. Maybe this is just a reflection of my bad attempts at simplicity. They often are structured around the assumption that you're touching a local video display. And so if you're doing them over a terminal protocol, they don't tend to. The simplicity means you're not taking advantage of all the nice terminal codes for doing scrolling at the right moment. And that's not universally the case, but that's often the case. So if I'm starting over and I'm gonna do this, well, I want to think, what do I need? Well, I definitely need modern sizes and layouts. I'm not going to be able to use it every day if I can't deal with 80 column text. I'm going to have to be able to transform text in all the ways that I do day to day in terms of the flow of text. And I'm going to have to eventually get things back out to disk with character returns because, again, that's what I work with. I'm going to want to be able to search. And this one surprises me, but something I discovered in this process is somewhere along the line, I don't know when it happened, I've become completely addicted to syntax highlighting. When I look at source code and it's not highlighted, my brain says something's wrong. I don't know what's happened to me. This wasn't always the case, but somewhere along the line. So for me, ultimately, that became a non-negotiable thing. So the first question is, well, what size blocks are really pages? Because let's reserve the word block to talk about these 1K pages on disk. I think 80 columns is going to be critical to me because of a number of things. Not least of which is, so I actually generated a histogram of all the lines of code in the Chromium code base to get a sense of, okay, I'm touching Chrome with this thing. You know, how bad is the problem? How many lines how big are lines mostly? Well, there's a big spike over at 0. A surprising number of lines have nothing on them. No surprise. And then a surprising number of other lines have 0 to 7 characters. And this is just because, you know, C code, you've got curly braces indented in multiples of 2. Not quite sure why there were so many at the odd numbers, but there were. And that's where the bulk of things are. And then from 8 to 80, it's actually fairly uniform. There's a fairly uniform distribution of characters there. There's actually a little bit of a drop off around 60, but the slope is very slight, and there's not that much difference between 8 and 80 characters in terms of the number of lines in that category. And the worst part is that the lines, if you look at them that are actually 80 or close to 80, they're all the worst kind of line, the line that you wouldn't want to wrap. They're a comment where somebody has meticulously gone to the effort of, let me justify this and word wrap this and do just the right thing to fit it into 80 columns. And so if I decide at 64 to go wrap that over, I'm not going to be happy. The other constraint I wanted to give myself is I wanted to work on top of 1K blocks. I figure that if even Chuck is using, in Colorforth, all the non-standard things there, I should be able to work with a 1K block underneath. And so what that really means is I don't want, for practical reasons, to have any one row span a 1K boundary. And then, of course, I need interoperability with text editors. So I need to have a way to go out to text files. I don't want to waste anything if I can help it. And this one really hung over my head for a while, and I eventually abandoned this, but and I'll talk about that. But I for a long time thought, well, I want to be compatible with this standard, and I struggled with that. So the first thing that I spent an exceedingly large amount of time sort of pondering on was, could I operate within a 64 by 16 space and do all the other things I wanted to do, and escape the long lines, wrap them, and mark, do something to squeeze them in. And ultimately, I decided, particularly given the comments and whatnot, that wasn't going to be doable. But my next fallback was sort of just as ugly because of a mathematical coincidence. You see, so if I've got 80 by 12, which is the most I can pack into that 1K block, well, look what's left over. It's 64. And so this, drew me in and led me astray. So for a very long time, I played with the idea of, well, I could have 64. I could have that first line of 64 be something that's just always 64, and then the rest could either be standard or not. And then what finally clicked in my head is that, well, wait a minute, though. The whole goal here is simplicity. I'm not, there's nobody that's holding me to this 64 by 16 format. So then I started thinking about some of those other constraints, things that I actually cared about a little bit, which is, ideally, if I'm going to operate, if something goes south with this, I want to be able to fire up, let's say, Vim and take a look at what's going on. If you've ever opened up a block file in Vim, it does crazy things. And so if I blow one extra character per line, I can throw a carriage return on the end. And it won't be great, but at least I'll be able to open it up. So that I can use up a little bit of that waste, and then there's 52 left over. So that's kind of nice, but the other thing is that 12 lines is not much. 12 lines is 16 lines is not much. 12 is just entirely too little, and I wasn't really interested in what kind of a world do I have when everything's horizontal. So I decided to go for a pair of two, and remarkably, that ends up with another sort of common size. You see 80 by 24, and then I've wasted the carriage return, but it's not really waste because I have leftovers anyhow. So this is what actually goes on disk, and this ultimately is just sort of the format that I keep my working state in, and I'll talk about that in a minute. So as I mentioned before, I'm hooked on VI. So I used VI-like keys, at least sort of to a first-order approximation. So the editor is modal, and there's navigate in an input mode. Now notice it's input, not insert, because one of the things that I also love about block editors traditionally is the sort of preference for overwrite. And I find that insert is a mixed bag. And so what I do I use the home row for navigation, but for insertion, I have explicit insertion. So if I want to slide something over, I tap Z, and if I want to delete, I push X. And backspace also does something sort of intuitive. And again, that was to encourage me to think sort of spatially and not get hung up on this idea of the flow of the text dictating where your cursor can be. And I added an extra, in addition to the sort of home row in VI, I added some single key shortcuts for word left, word right, and then page up and page down on the row below it. Kind of a little bit like the Colorforth editor, but sort of turned around a little bit. And then for copy paste, I did something I've done in every other block editor I've done, which is sort of the poor man's copy paste. I have a single line copy where I do, if you copy once, you get one line. If you copy again, you go line by line, and it fills up your clipboard. And if you move around, then you've committed yourself to whatever chunk. And that's worked okay. And then this is another weird thing I played around with far longer than I should have, circular wraparound. So I had this notion that with all that extra space, I could do something clever, and of course, cleverness is foolishness. And I was thinking of things like, oh, let me do linked lists of blocks and things of this nature. And so I got this idea of, well, I don't really, particularly when I'm editing a large document, particularly care about block numbers. So let me treat this as a big circular buffer, and I will use search to find things. And if I was loading from these blocks, I would expect some kind of an index. So for better or for worse, I thought that it would be a simplification of dealing with this to treat it as a circular ring. I'm not sure that actually worked out in practice, and you'll see how that looks in a bit. But that's what I did. And the reason that the circularity thing matters is that although it's a block editor, I show adjacent blocks, and you can move vertically a line at a time. And so I highlight block boundaries by changing the background. And again, you'll see that in a moment. So to import and export, I use escaping. And as I have been often want to say, escaping is the root of all evil. So I'm courting evil here. But the way I do this is I use all those other characters above 126 because who doesn't use just ASCII? At least sure I don't. But so I grabbed a number of them and used them for special purposes, which I'm sure will come back to haunt me in all sorts of ways. So I have a start of file marker to indicate that I want to represent in a block space some file that I've brought in from disk. And then I have an end of file marker, and I visually represent them with dollars and tilde, but they're internally stored to some other character. And then this is the really important one, is this continue line marker. And again, it's a special character, not an actual slash. And the idea is that when you have a normal line with no continuation marker, the assumption is that when that is serialized out to disk, you will trim it, and there won't be any trailing white space, because in the code bases I deal with, that's the default. So in a normal line, you just see a normal line with white space on the end. If you actually wanted the white space, you might put the continuation marker to indicate that here's the line. But the other reason you use the continuation marker is to wrap to the next line if you did actually have a line that was over 80. And even in the Chrome code base, where ostensibly there is a restriction on lines greater than 80, there are a sizable number of lines that are actually greater than 80. And so this allows me to pull in a file from disk into a series of blocks, and it always comes into an even number of blocks, and then make edits and then write this back out. The other thing, since I had all these extra characters, I added some color markers, and the main reason there is actually motivated by this slideshow, which, as you may have guessed, is in the editor. So yeah, I wrap lines over 80, and I load the file into a range of blocks, and then I can save out the file, or I can drop the file. And what this ends up doing is that my block space becomes not the primary source of truth for things, but rather is my workspace. And so I have this persistent workspace that I can bring files into from a range of places, and then unload them when I'm done with them, or keep them around if I think they may be still relevant. And particularly as a VI user, where I have a tendency not to keep a persistent session, or where I want to enter my editor and leave my editor, I've actually found this nice, at least so far, in that it sort of gives me some of the things that I find that, say, an Emacs user might want, where they keep the session going and keep a lot of state, but in a form that I can cope with because I can come in and out of it. And I have sort of a little more direct control over what I keep and what I don't keep. But one other wrinkle this produces is that in order to be able to edit source code that's intended to be able to shrink and grow at any given line, I potentially need to be able to split a block. And then I'll show you how this works in a bit as well, but these continue markers become critical in order to split a block to allow you to insert things in the midst of a file. So search, I went back to block editor 0. I added a fourth command prompt. Excuse me, a fourth command prompt. So when you hit backslash, you get just a fourth command prompt. And I use some single letter commands to do things like search and to edit a file and things of this nature. And then I have some shortcuts. So if you hit /, you get the command prompt where S space has been inserted, ready for you to do a search. And one other quirk, because you're spinning up this block file, what I do is I just keep a dot file that actually is the block file at the root of whatever workspace I'm using. And so the idea is if I'm editing Chrome, I'm up at the top of the Chrome tree. I have my block file, which has all my working state in it. And then I'm pulling in the files I want to edit and dumping them out as I go. And so the editor, or the command line tool, rather than loading a file name when I type it, instead I have a search phrase so that my editor is block editor 2, and if I'm looking for something, it will bring me to that symbol that I'm looking for, things of that nature. I try to work nice with the terminal. I've discovered that every terminal, every contact, I use a surprising number of different terminals, but all of them remarkably pretend to be an Xterm color. They're not actually. I've found all kinds of interesting wrinkles in their compatibility, or particularly around a point I'll mention in a moment. But the nice thing that an Xterm color brings you is color, and so it's actually got a fixed palette that's kind of nice. You get your sort of usual 16 colors, and then there's 216 of all of the RGB at 6 different levels in all combinations, and then 24 shades of gray. Yes, well.
Off by a factor of 2.
Yeah. And I try to scroll whenever possible to avoid having to repaint things that I don't want to repaint. And there's a property that I actually had a hard time finding. If anybody can figure out what the proper term for this is, I've been calling this sort of row select. But what I mean, and I'll just show it to you. So if I select with this cursor right now, you'll notice that each character is individually getting selected. But if I turn off those margins, because I've taken extra special precautions, the rest of this line is treated as a single entity. And if I were to copy and paste this to the clipboard, I would actually get I would get carriage returns here. And it seems to be incredibly non-uniform how this is handled in different terminals. And so the OS X terminal, for example, is unusually fussy about what you can and can't do on that line if you want it to preserve the behavior that you can select the line and copy paste there. And so I've ended up making the margins an optional feature explicitly because on OS X I could not find a way to allow you to have any kind of highlighting and still preserve this property that when you cut and paste you don't get extra, you get spaces.
I think it's called line select. I remember working with, I forgot the ANSI standard. It's 3 dot blah blah blah.
Line select.
It's the old BT100 stage sequences.
Okay.
So they just hit me up on this is like line select.
Line select. Okay.
Right here and then go.
And it's really odd with OS X. What's really weird about its terminals, there's these commands for, fill out, move the cursor to a location, then you can say fill the rest of the line with the current color. And in many cases, if you haven't actually emitted a character, OS X will just ignore you for their terminal. Other terminals don't do this. I actually use a wide variety. I use the GNOME terminal on an Ubuntu desktop. On the Chromebooks, I use this JavaScript implementation where I at least know where the guy sits that writes it, so I can go harass him when there's bugs. And then, but anyways, so line select. Thank you. That's helpful. Yes, but and the weird thing is it does, at least with OS X, it doesn't seem to be the carriage returns and line feeds that it's taking into account in deciding this. It's something else that's going on, but I'm not quite sure what. Certainly, if you just emit text and do ordinary line feeds, it does the right thing. But it seems to care a little bit about what was in the buffer previously on that line. Anyway, so syntax highlighting. This was the one that sort of surprised me. And in fact, I spent all this time vacillating over a format of blocks only to ponder what would I do with syntax highlighting. And it came down to just, to me, uncolored code looks weird. And traditionally, some rather severe techniques are used to do syntax highlighting. Folks will use regexes, and they will have elaborate systems of rules. And basically what they'll do is they'll attempt to mirror the language grammar again in some configuration file particular to the particular editor. And even then, despite all of their great efforts, it often fails. Particularly formatting for Forth often just does not, you put a character where somebody didn't expect that in their regex, and all of the syntax files I've seen for Vim tend to fail. And this has even gotten to the point that I've heard of efforts where folks are wiring up Clang and actually, trying to use actual compiler front ends to do their syntax highlighting. So it's complicated and scary, and that is not what I want in my editor. I don't want to drag in something big and complicated. So there's this other idea, and I had this idea independently, and only later learned that other folks had the same idea, and there's a name for it. It's called semantic highlighting. And the core idea is that you want to show like things in like colors. You can still use syntax knowledge. You can still do a hybrid. But basically the goal is that if you've got a variable in one place, if you have that same variable someplace else, you want it to be in the same color. And ideally it's stable between files. So if you've got foo in file A and foo in file B, they should still be in the same color across files. And to my surprise, after having done some actually looked into this, though I use Visual Studio, I do not use the IDE and have not fired it up in maybe a year and a half or so. And apparently, even Visual Studio has acquired an option for this feature, as have a number of the other editors. So apparently, it's become a thing here in 2013 or so. And the really great thing is that it's easy to approximate. It's actually fairly straightforward to get it mostly right, without a lot of work. So here's my easy semantic highlighting. So all I do is I classify all the characters in the character set as either being identifier characters or as single characters. And I break apart words at spaces or at the single characters. And then I hash the word. And I derive the color that I want to assign to the word from the hash. And I allow one other thing. I allow the notion of a stuck color. And so certain words, and by words, I mean strings of characters, trigger the current color that you're on to stick for some duration. And then certain other words will unstuck them, and you always unstuck at the end of a new line. And I make one small concession specific to Forth, which is Forth is weird in that it's using parentheses for comments. And I'll show you this in context in a moment, but I found that it was useful to detect lines beginning with a colon on their own and assume that they're Forth-like, and assume that I might want to treat parentheses differently and treat them as a comment character only for Forth. And it actually works pretty good, or at least yes?
You mean big hash to avoid collisions?
Yes. Yeah, it works surprisingly well, at least for Forth, C, C++, and Python. Maybe my sensibilities are not your sensibilities, but I find that it meets my needs in terms of.
Do you hardwire something like open? I imagine open brace and closed brace, you want to be the same color.
Yes, you've actually guessed that. There's I do actually a sweep through the character set, and I convert several of them to be treated as the same character. In fact, exactly those pairings. So yes, that's a subtlety I didn't bother bringing up, but yes, in fact, that was a little nitpicky thing. And the other great thing about it is it works for mixed language stuff. So if I've got a big buffer full of some C code and some Forth code, it's independent of the language. In fact, each line is independent. And it's stable across files because the hash is stable. So here's what it looks like for some Forth code. It's very colorful. But you'll notice that one thing that's nice about it, after a while, the comments, of course, are their own thing. But like, take a variable here, like this hash value. Immediately, it jumps out at you. Oh, here's where hash value is in the file. And so you can see where a word is used. Or if you take like a word like this normalized character, you can see at a glance that a word of that size and that color simply doesn't appear on this page. So it's clearly something that's coming in from the outside. And so it helps you see things that are the same and things that are different. And really that's sort of all I at least find that I'm looking for from syntax highlighting, is some extra amplification of differences that would otherwise require me to sort of parse whole words. And so you highlight keywords. I ended up keeping digits as being different because I found that even having a constant that appears over and over, it's helpful to see, well, here are these 6s. oh wait, there's the 5. That's one notch less. But part of why I went to the trouble of treating comments differently, and this I think has to do with at least my propensities in terms of forth. I find that I wish I have this belief or hope that hope is more like it. That in really good, really expressive forth code that a stack comment might not be needed. But I find that in practice, if I don't have one, I always regret it. And so for me, stack comments are this one concession to sort of, I wish my code was expressive enough, but I know it won't be. So I will put it there to ensure that I don't find myself scratching my head later. But really, it introduces noise. And so while it was kind of interesting when these were highlighted with their own colors per type, I found that it was just noisy. It wasn't. It's like I don't really care to see the type information there. I'm only putting that there as a note to myself. It really is a comment. Whoa. No. Okay. Lingered too long. Come on. Is that going to come back at any time here? No.
So much for Apple.
Yeah.
You could probably turn those timers off. When you're presenting.
Okay. So here's what it looks like with C code. And again, the same pattern occurs. You get, oh, here's argv, and there's argv, and there's argv, and there's argv. Or, oh, I pulled in this extra knuckle nano main, and there it is there, where I'm using it. And so to me, I find that this is about what I'm looking for. I'm looking for the comments to be obscured so that I notice, oh, this is a human readable thing. And then these symbols, I actually find this useful. And so at least to my eye, that was what I was going for. Here it is with C++. Again, here's a request, and oh, there it's used there, and it's used there. And oh, there's the reply, and it's used each of these places that jump out at you because you can pick them out. I'm curious, by the way, because I'm picking colors that are randomly scattered throughout the spectrum. How does this look to a colorblind individual? I'm assuming that it still has some utility, and at least as much as it does to me.
It's complicated. It really doesn't, because color has so little, I de-emphasize color. And therefore color does not have the effect. It does not have an emotional pull. There's
Interesting.
no emotional attachment with color, other than yellow.
Other than yellow.
Yellow is just weird.
Huh.
But yeah, it doesn't, to me, this is just more noise.
Interesting.
Uh,
Well, blind people are very simple. All it takes is this one infinitely long line. If I want to skip it, just skip it sentence. So their method takes so long and takes just one more.
Indeed.
There we go.
So I'm actually not colorblind. But looking at the C++ code, all I see is a wall of text. Like you pointed out the different locations of the request parameter. Without you having actually identified it where with the pointer, I wouldn't have seen it.
Really? That's interesting. So you're
Also, they don't know what color it is.
clearly I've made the editor for me.
And that's not a bad thing.
Indeed.
Chuck did the same thing. He doesn't realize that he did, but that's what he did. And color is personal. It is not discrete. Colors are not discrete.
Yes.
From one person to other, without even being colorblind. Colors are not the same.
Yes. Yeah.
I should point out that I respond much better to font than I do to actual.
Interesting.
I mean, color does still have an impact, but I see this as more like abstract art than
Interesting. I actually dabbled with introducing a little bold and underline, and I found that for me that was actually less informative because it was a less severe sort of like, oh, now I have 2 dimensions I need to match things up on, and then
right. And you have to understand too that when I say I respond better to font, I'm talking about like
old school Algol type setting.
Hmm.
Like that code, it just magically starts coming out, and it's like, oh, I can see the structure, I can see everything, how it maps together. But yeah, color doesn't give you.
Color isn't doing it for you.
Yeah.
Any book on graphic design discusses fonts, font sizes, and never discuss color and underline as a way of conveying.
It's not consistent.
Yes.
I'm worried, just.
Why do people know what
For the letters versus the color of the text. I always, for the symbols.
Mm-hmm.
That's more important than color, because I just look at the words when I
Mhm.
know what the beginning and end of something exists.
Mhm.
More so than,
No, it's a fair point. I mean, I think I'm getting a little benefit, in my at least from my eye of it of seeing the highlight of the symbols, but to me, I guess surprisingly, I find I care about the identifier names is why. Mhm. Yes. Oh yes, the highlight to matching pairs, and I haven't actually done that, and I've toyed with doing that because I occasionally find that useful. Of course, that's harder because then you have to actually know enough to parse it correctly.
Another problem you're going to have anytime you do color
Mhm.
is this is different than paper,
Yes.
and you can't remove that.
Yes. Yes. Yes.
It just won't work.
Oh yeah. Oh yeah.
And so it's not portable.
Yes. 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 Indeed.
Braille is part of it.
But anyhow, so I mean, sadly to say, and I do wonder occasionally your observation, Sam, that this feels a little like noise to you. It is perhaps an indication that the syntax highlighting that I get normally may to me be just a sort of a comforting background noise, and this satiates that desire. I'm not sure, honestly. It's artsy, yes. So.
Well, I'm not saying that this doesn't work in all cases, because I just did a Google search, and there's a huge number of people out there that are really into semantic highlighting.
Yes.
Now, what I'm kind of questioning right this moment is what would it look like semantic with a font chosen by so
yes.
monospace versus proportional width, serif versus non-serif, bold versus non-bold, that sort of thing. How do they play with this? I mean, I'm kind of curious.
So something I've been surprised by, at least what little searching I've done. A lot of the folks doing semantic highlighting, they seem to actually restrict the color set more to a smaller number of buckets, which kind of, well, I actually played with that, and I found that I was, if anything, I was sad with the limited number of colors I got from Xterm Color, because what I most don't want is false positives, right? It's like, oh, the post message and reply are, I'm glad that there's that little tiny difference there. I wish it was, yeah, I wish there was more, right? Because it's like, that's a different symbol. I want a slightly different color for it. And so there's a number of folks out there where they're working with maybe 5 colors, and it's like, half of everything's false positives then. Yes. Gradients, there we go. Make them truly unique. I'm sorry, I interrupted you. You were going to. I need. But we'll see. I've only had this in a form where I could use it day to day for a short while, so it may slowly drive me mad. I'm not sure.
There's also in the real programming world, there's a whole bunch of people now that have automatic documentation tools, which will put your code in one column and comments in the other, and then do this thing. They also tend to change fonts and bold certain things like method calls and functions, and it's becoming popular. I'm not saying it's the right way, but there's group of people who seem to really like that.
The other thing I should mention, at least with semantic highlighting as it is generally done, is that I am definitely doing the poor man's version. Usually there is an emphasis on even deeper analysis of the code, and maybe, you know, do you figure out that this, you know, this variable really is the same variable, and, you know, same place in memory, this kind of thing. So there's all kinds of, I'm puzzled though why you would pair that with then having 5 colors to work with. That to me seems.
Now, something like this, I could see working in a dynamic fashion.
Mm-hmm.
Put your mouse over a word and then highlight
Everyone else that, yes.
That might be useful.
Perhaps, although I mean, again, a part of what, and it's interesting to find that you all are not sort of. To me, I'm able to sort of scan and survey it. It's, oh wow, okay, self is there, there, and there, and that makes it jump out to me, which is interesting. That yes.
Did you use star and hash?
Did I use star and hash? Yes. You mean as for comment characters? Sorry, no. Sorry.
Yeah, that's the word match. So star takes you to
Y- Yes. Yes, I generally did not. So.
It actually starts, when you put the cursor on a word, you hit start, says I'm going to start searching for that word.
Mhm.
Start says go down the text, and hash says go up the text.
Oh.
After you've done that, all you have to do is hit enter.
Ah, I did not know this. Interestingly.
When you do that, you get the same effect. When you put your cursor over key, for
Uh-huh.
example, press star, and it cycles over all the.
Ah, cute.
Going down.
You get the same kind of effect.
Uh-huh.
Perception of where all the same words are.
Mm-hmm.
As you get like looking for.
Right.
Why is it that every color seems to be either pink or purple?
This.
I'm green and everything else is.
Well, I think it's that particular file. There's actually quite a lot of redundancy, right? The word return is occurring, and it had memo, but by bad luck ended up in the same spot. And that's the trouble. Is that one thing I struggled with is that you've got this uniform color space in 6 steps in RG&B, and you probably don't want it to be uniform in terms of you know, the space that people perceive as being distinct. So that may be an aspect of it.
One man's editor. One man's editor.
Indeed. All right. So as you, this is neat. This is neat.
But here's the thing, though.
Mhm.
Like with something that's like super simple, you could like I could download BE2, for example, and make changes to it so that its coloring or whatever matches my preferences.
Mhm.
Like trivial.
Yeah.
Yes. You know, I built 5 specifically. It's the BI like block editor. And it's composed of like maybe 16 blocks of code at most. It's been like almost 12 years since I last.
Yeah. Yeah. The date was 2002 or something on it. So it was ancient.
The fourth Greek wiki has the source code now.
Yeah.
I don't even have my own copy.
And you did mention
Yes. 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 Indeed. So I've been using G4th, and I've kind of baked in, unfortunately, G4thisms. I cringe to think what would happen if I ran the ANTS compliance test. I'm sure I would fail. It's 800 lines in what I would like to call block normal form, which is to say, I originally had it as just continuous source, and then in my block editor form, I wanted to make sure that I had structured it around the block boundaries, and that padded it out. It was only 600 lines before that, so this added some dead air, but I think it's well worth the clarity. And so that's about 32 pages of code. So, and there's definitely more room for refactoring. There's always more room for refactoring, and there's slideshow support, which you may have noticed. So now I'm going to do the code tour. So as you may have guessed, I'm already in the editor, and let's see. What I will do is, oops, that's search. So this is the command prompt, and I can do forth on the command prompt here, of course, and get things back. But more importantly, I can go and edit the source code. And what I just did was by edit it means to pull in this file, and so you've got that beginning of file marker here, and this if I want to write it back out, I just hit Shift W, and that dumps things back out. So I can move around, left and right and up and down and all of this. And then I can move, by word, forward and backward, or by page, up and down. And between blocks, yes. So I've vacillated even within the source code. Originally, I used the word block, and then it dawned on me I'm conflating that with disk blocks. And so I've started using the word page because it's a non-standard thing, and my intention really was a page. The other thing that I allow, I'm on the fence about the virtues of this, but you're allowed to cross the boundaries, and so that slightly darker background line is the block boundary. This is not so useful with block-oriented code, but is useful with continuous code, which we'll maybe look at in a minute. So let's just do the 32 blocks. We can easily do the tour. So there's a page full of constants for those continue characters and start file characters and all of that sort of thing. Here's the core state of the thing. So there's I vacillated as to how I wanted to represent the state of things. That I have this top variable, which is the line number in the file of the top row at any given time. The caret is the offset in characters from the top. And then the input mode is just a flag for whether you're in navigate or input mode. And a page of code to handle the external color escape codes. And you'll see again, so this is one of these things where it's like, to me, oh, there's that escape, and it just jumps out at me. Oh, all the places where I used the escape word. Here's those background colors. So there's I've got the body color, which is here. I've got the title color, which is that line, and then the margin color, and then the prompt color is the color behind the prompt. Here's all it took to do the classification of characters into buckets, and here's exactly that step you predicted, James. The conversion of these characters so that their hash is the same, and so that they follow out nicely. And then here's a similar thing where I make the continue and start and end file characters printable. And a critical string operation, rtrim, to trim off the spaces at the end of a line so that I can, because that's used all over the place. Oops, I went back. So here's the computation of, and this is actually that page we had up before. It's the computation of the hash of the word. And originally I used a different hash function of my own devising, one where you use 3 values. And I actually wish I had retained that, because one of the nice things is that, if you have, say, several variables with different names like this, and oh, that didn't work out nice. See, this collisions kill me. But you have different names, and even with a small difference, you get different variables, which I find helpful for spotting things. But as you say, that's to each man his own. So let's see. We did that one, and here's the word hash computation. I also have to buffer the words as I'm hashing them, because I want to gather up the hash of the word and then print it. And then this is also where I do that the state management for the sticking and unsticking. And then here are the rules for when I stick and unstick. And so I have some of the characters that that trigger sticking and unsticking in various patterns. And then here's that colon turning on 4th, so that I know that this line is 4th. And then there's a little bit of a state machine there to introduce the behavior I wanted for the comments and things and strings and things of that nature. This is then the main routine to emit a single character and then a string highlighted in this fashion. Here's the command prompt handling. I found what I'm almost certain is a bug in G4th's except keyword, or actually there's a word that they have in their docs called edit line, which is supposed to be a variation of except that allows you to provide the initial value of the prompt. And unfortunately, if you provide an initial value, it screws up. It screws up if you hit backspace. The redraw is wrong, and so I put in a hotfix workaround here to that. And so this is the plumbing that lets you pop up that prompt and enter 4th commands. This is the meat of accessing rows, and it's actually more grisly than I would like. This is the initialization. So when I create this thing on disk, I want to be able, and I'll show this in a moment, I want to be able to open up the block file and have a full line and then the carriage return, full line and the carriage return. And then when I get to the very end of one block, I need to pad it out with spaces. So you get 80 character lines until you get down to the long line at the end of every 12 lines. So there's a little bit of dance to initialize that. I had hoped that the wraparound, the fact that this is a continuous ring, would simplify things, but it actually didn't. It hasn't seemed to. There's a whole bunch of places where, if anything, that means you're not sure. Oh, do I need to throw an extra mod in here? That sort of thing. Here's the handling to turn on and off the margins. The margins are kind of. I wish I could have the margins on all the time because I want to see where that 80 column boundary is, so I know how big my canvas is spatially. But if I have it on, I can't do the copy paste, as I mentioned. At least not on all the plot. There's actually, of the 3 different terminals, there's one of them that I can have the margins on and copy paste successfully.
Sorry, could you converge on
yes.
Within 10 minutes?
I will do so. I'm over time. Awesome.
No
all right. So here's the drawing of the screen, and here's the caret, the movement of the caret, and I've got simple words for left and right, and everything goes down to this caret plus equals word that lets me navigate a character at a time. Here I'm able to do word left and right, all that sort of thing. Here's inserting text. Here's this. So all of the code to import into this format from a file on disk is just these 2 pages, and this lets you navigate and find the beginning and end of a file. And then here's export. Again, two pages of code to convert from the standard, our standard on disk. And then here's code to let you drop a file that you've imported previously. Here's search, and here's the code to do page splitting. Let me quickly show what that looks like. The idea is that suppose that I wanted to insert something here. I have some additional thing I want to define. If this was a continuous document, I don't want to have to reflow the entire set of blocks. So what I do is I can split the block and have these continue lines, and then I can insert my additional code here. And when I save, those continue lines will get collapsed away. But for the duration of one edit cycle, I've got this extra space to work with. So
how does that handle cross-block boundaries?
It spans blocks. It goes. I mean, it continues on to the next. Yeah. The issue. So all I'm doing there, I'm not actually. I still have to grow the file, which is unfortunate, and actually shift down the blocks, which I'm not happy with. This is why I toyed with a linked list of blocks originally. The main thing that it buys me is it means that I'm not shifting somebody so they're no longer block aligned if they previously were. Here's navigation between pages and adding a page. And here's the page of the clipboard handling, the way that works. I'll show you on the next page. So here are the one-letter shortcuts for editing, searching, and all of that. And say I want to copy them. Well, I hold down my copy key to copy, and then I can paste it back out. And if I want to, or I can cut and then paste one section out. So it's a sort of a very primitive sort of copy operation. So here's the common keys that are active all the time. I've left the arrow keys working in all the different modes. I find I don't use them. I've been doing VI too much. But something I always liked in the block editors was, you can type and navigate and move around. And I'm hoping I'll fall into the pattern of that. Here's things that happen in input mode, and here's the things that happen, all the keystrokes that are available in navigate mode, sort of splayed out. I toyed with using the pattern you used in Vibe of using the dictionary itself to represent these. And the thing I found unpleasant was the need to sort of encode the ASCII code of the word. And I struggled with what I really wanted to do was something readable, but I didn't want it to be any bigger, and I certainly didn't want to have to sort of name it once and then. So I struggled, and I finally went with the case statement for lack of any. But it bothers me. And again, here, there's that nice symmetry of and end of that I suppose a more intelligent syntax-aware editor would somehow pair those two in a more cohesive way. But to me, that at least makes them all stick out. And then here's the main loop and the setup and deciding where that block file goes, and that's the whole editor. So, for example, if I exit out of the editor, or the way you exit out of the editor, if you actually desire to fire it up, is you hit Control-C, which I found was simple enough. It's saving your state as you go. Let's not do that. I'll show one more thing here. So, I don't have a Chrome source around here. That's the trouble. Nope, and I don't have that. So say I'm in some checkout of code here, and I'm going to fire up my editor, and I can pull in a document to edit, and oh look, here's this little snippet of thing, and I can look around and say, oh, and I want to open up the make file. Let me do that as well, and I'll open up the make file. And so now I can and I've got my editor here as well, my slides here as well. I must have opened them previously in this session, and I can search about for them, and I can say, oh, where's main? Do I have main? Oh, I don't have main. Let's see, is there my name in here somewhere? And I can jump to the appropriate place in my document. So that's that. And let me exit from this session and go back to the other one. Oh wait, So I'm still in the same session. I'm confused. Where's my slides? There we go. So future directions, which I'll quickly run through. I probably will refine the keys. I'm not completely happy with them, but that's how it goes. I'm likely to add, undo, and redo. I don't have them. Been leaning on version control. That'll make me sad. I know it will. I would like to add an overview mode where I show the top line of each block, and so I can sort of navigate more quickly. I'd like to enhance the clipboard. At least preparing the slideshow was a little tedious. It wasn't too bad. I'd like to add a spell check, but the big thing that I want to do right there is I want to keep it simple, and yet I want to somehow do something about the problem that I have with all spell checkers, which is that they don't understand identifiers in source code very well. And I feel like there ought to be some simple, easy solution, but I may be misleading myself. I'd like to document it better, and particularly, which keys do what for someone other than myself. And I would like to add inline program execution. I'm very covetous of things like eShell and Emacs, the ability to sort of meld your running of programs and your editing of documents and your editing of their output. And I think there may be some natural pattern that I can add here that's easy and straightforward. Questions? And I'm well over time. I apologize.
How much use have you given it?
I have only really been actively using it for about a week. So.
Do you find yourself reaching your own editor when things get?
A little, not since I started before I had the syntax highlighting. That made me not want to use it. So for me, the color really actually mattered. It's sort of shocking and strange given that, particularly, I'm surprised by y'all's reaction. I'm appreciative of that. But for me, that was the deal breaker. Actually, was like, but I want my color, and I don't. I think that must just be some animal response to it. I doubt that I'm actually getting that much practical value out of either this highlighting or the other highlighting. So clearly, it's a flaw. So I'll let you know next month. That'll be the real test if I can actually use it for a month. Yeah. Mm-hmm. Yeah, and then I think. Mm-hmm. 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 Yeah, it will be interesting to see.
So when you edit some file which you're sharing with the co-workers, you're going to be leaving block, or it's going to start on multiple.
So it'll depend a little. So because I have the ability to do that block split that I showed you, I can retain the flow of a linear document. And I'll almost certainly have to do that for documents that I'm collaborating on.
So how will those sessions work? You give it to it, they'll check it in, and then
So when I save back, so I load it into my block buffer. I do my thing with it. I keep my state. When I save, it goes back out to a normal text file.
But then some other person edits it,
Uh-huh.
and then you've got your own block version.
Oh yeah, no, I have to assume that if I'm going to sync, I need to dump out the blocks that I'm using. So I have to be careful with that. Yes. We'll see how that goes as well, because there's danger there that, but again, I'm almost always using version control, so it's unlikely that I'm going to, I'll save and then wait, no, that's the old version. Yeah, that's not. Yes.
How do you just something here, language control, version control?
What's that?
Just version control is probably different.
I mean, the nice thing is that typically if I save something back out and the diff is far more than I expect, I'd be, wait a minute, I must not have get the state. So I have a little bit actually already, just even, by the way, the code is up on GitHub, and pushing up the code to GitHub. One time I actually did have a stale copy of the slides, and I was like, wait a minute, I didn't change the slide. I changed one thing in the slides. What's going on? So I have toyed with the thought that I might add a date stamp or something to the to that file marker at the beginning, so that it can scream at me if the file is stale. But of course, notice how this slowly slips into the realm of being a sort of, I'm keeping multiple document whatnot. So
Actually, it's actually relevant to a book that I read a while ago called The Humane Interface by Jeff Raskin. You may want to read that because he describes what he calls the humane editor. It has a workspace concept that is almost identical to this, right down to using dedicated codes to represent this is the start of the file, this is the end of the file. And you navigate basically your entire working set using nothing but search. And you can also include start a file marker in your search queries. So you can actually jump directly to the start of the file. In fact, that's how file names are just convention. It's basically start a file marker, like a name, and then everything else is all the same.
Right. And in fact, the way I create a new document is create a new block, start a file marker, file name, and then I've got my. So.
Testing, 1, 2, 1, 2. All right, so I'll be starting here in about maybe 3 minutes. Hey everyone, I hope I'm streaming audio. My name is Sam Falvo. What's that? Yeah. Normally I have like some kind of slide presentation or whatever, so I'm just going to be doing this from a text file here. So, Kestrel 3 update, the machine language monitor now tokenizes its input, so it can actually identify individual words that you type into the command line. It does not act on those yet, but baby steps. I figured once I was done with that, I can spend the rest of the week just kind of hacking idly on an idle curiosity of mine, which was how can I make best use of the RISC architecture chip in the context of Forth. So we've got all sorts of techniques for converting programming languages that are represented in abstract syntax trees into relatively efficient code for RISC machines, but not so much on stack architecture code. A little bit of Googling has revealed that there's a renewal of interest in peephole optimization. So I figured, I'll give that a shot. So that kind of kickstarted this project. And it comes from several observations. One is that the MISC and RISC concepts have very similar numbers of transistors when it comes to actually doing something with data. For example, and you can you can kind of gauge complexity of the execution units by the types and the numbers of distinct instructions that they have. So here's an example. We have the F18A by Green Arrays, which has somewhere in the vicinity of 32 opcodes. You could argue that it has slightly more because there's a range of addresses that when you branch into, you get a slightly different behavior on some of them. But somewhere in the vicinity, 2 to the 5 power, that's more or less what you get. The RISC-V architecture, specifically the 64-bit integer instruction set, because there are other modular instruction sets that you can add on to this, but this has fairly close to 50 instructions all total for 64-bit computation. Now, I'd like to contrast this, especially against some of the more popular processors throughout history. The 6502 has a very small number of instructions, but there's over 20 addressing modes involved. So you can kind of think of these as modifiers or tags to a particular kind of instruction, which, as you can well imagine, greatly complicates the implementation of the execution unit. It's not something that you can just look at one number and say, oh, I need to do X, and then actually go and do it. The 68000 has, now I hand counted 87 opcodes based on the Motorola's CPU 32 manual. But I know that it also has a little bit more than 8 distinctly different addressing modes. I believe the actual number is something like 12, thereabouts. But the 80386 takes the cake. It has over 300 opcodes, which you can tell because these opcodes are bytes that are independent from the actual byte that says what the addressing mode is, and there are almost all 256 of the 1 byte opcodes are taken, and there are several sets of 2 byte opcodes. So you're looking at somewhere between 300 and 600 distinctly different opcodes. And on top of that, there are over 50 different addressing modes when you count them all up and you multiply all the bits together. So the 386 by far is one of the most complicated execution units that you can hope to get. So where MISC and RISC really differ is where do we find our operands from? So if I want to add 2 numbers, where do I get these data from and where do I put the datum back? And yes, I said datum. I used the right word this time. So that's really the motivation behind me kind of wondering that I should be able to cycle match on average MISC and RISC programs. In other words, if I were to take the same Forth program and apply it to both MISC and a RISC architecture, I should be able to get comparable performance from each. The trick, of course, is how do I do this in an efficient manner? Because the RISC, or more precisely, the question basically boils down to is how do I utilize the RISC instruction set's register set in the same manner that MISC would use its register set organized as a stack as closely as possible. So the goal here is to write a code generator that at compile time allocates registers as closely as possible as what MISC would do at runtime. Now, managing expectations, of course, a compile time system never has the complete picture. By definition, it cannot. So therefore, we know that the compile time system will always fall slightly short of what we would expect on the MISC architecture because the MISC has that extra runtime context. However, I think I do a pretty good job of coming very close to equaling MISC's performance. So we start off by defining a virtual machine model. Many people will actually be familiar with this type of machine model from, say, for example, Pygmy Forth. It's very similar in the sense that we have Let's see, we have a data stack cache, and then we have a data stack pointer. So in other words, this is a fairly traditional direct threaded fourth implementation. However, we extend that. I have a return address and a return stack pointer. So basically, I maintain two separate stacks in exactly the same way. Now, this is actually imposed, this is actually an imposition by the hardware. RISC-V instruction set does not define a hardware-defined stack. So everything has to be managed in software. And you'll see later on why I chose to implement it this way. Then we have 25 registers available for allocation to hold intermediate results during a computation. These registers are allocated on an as-needed basis, and they may map to a data stack or to a return stack item, especially when you get pretty hairy computations that uses push-pop or 2R from R, depending on your dialect. We have a global pointer register, which I won't discuss in this talk, but it is used to hold large, or it is used to refer to large constants. And then, of course, the program counter. So we start by recognizing that there are two basic stack operations. One is you push a value onto the stack. This is actually pretty simple to do. If the register is available for use, you just grab it, you mark it as being used, and then you emit whatever instructions you need to populate that register with the data that you expect at runtime. If not, you have two choices. One is you can generate an error, or you could spill a register to memory and then reuse that register later on. Personally, since this is just a toy implementation, I just went the simpler route of just generating an error. And when you think about it, having 25 items on the stack at once is probably not a good idea anyway, but something to think about. Now, when you consume an item or pop an item from the data stack, we have two possibilities. Let's assume for the sake of argument that we have at least one item in a register. That is to say that something has fairly recently been pushed onto the stack. We can actually, the compiler knows exactly which register this is. So we maintain a compile time stack of which registers map to which data stack slots. So we can actually take that register and actually use it in an instruction without fear of knowing, hey, is this register live or dead? We have no need to keep track of that information because that's implicit in the stack-like runtime. And this includes the data stack cache, by the way, as well. So we'll see examples of how this affects the code a little bit later on. Now, if no more registers are available for use, then what you want to do is, generally speaking, the only time that this would ever happen is if you start a colon definition with something that consumes its inputs. So, for example, a drop, or if you execute a naked plus, for example. A good example would be like the definition of square that Brad had used, where you have dupe star. The dupe, of course, takes one item from the stack, produces two, and then the star would actually multiply those two items. But that dupe has to get that data from somewhere, right? So what you do is you actually keep track in the compiler state where you think the memory resident portion of the data stack is, and then you can maintain and keep track of offsets from that base. And so what you do is, if you actually need to use the value, you can actually fetch it into an available register and then operate directly on that register right away. And it has the benefit that you don't even need to keep track of you don't even need to be able to say, okay, this register is allocated because I'm just going to use it and consume it right away anyway. But otherwise, the important thing here is to make sure you understand which offsets are currently being used. Once you have that down, everything else falls into place. Generating instructions is piece of cake. You just append them to a list, and then after every operation, you vigorously optimize that list. This is, of course, analogous to a shift-reduce parser. And in fact, some of the research that I've seen online indicates that this technique is called a shift-reduce peephole optimizer because of that, for that reason. And it basically works the same way. When you're actually taking in data, you put it onto a temporary buffer of some kind, typically a stack, and then you, before consuming anything else, you actually minimize the state of that stack or that buffer before you actually continue processing. So this is actually the pseudocode behind how everything works. To optimize, like I said, you perform a single optimization and then you keep on doing it until you can't do it anymore. And of course, the individual performing a single step is very simple. You take a pattern of some length. You check to see if the most recent n items on that instruction list match that pattern somehow. And if so, you replace that pattern with a specific replacement. So here's a very quick example of the body of the optimizer in the code. It is written in Python, but I will go through and I will actually let me just open those up there for easier reading. So basically, here's an example where we're going to check to see if we first compile an OR immediate instruction, and then we compile an AND instruction, and then there's an additional constraint about the registers. So in this particular case, if one of the sources that we're using happens to be the destination of the previous OR immediate, we can actually collapse both of these because they're exactly the same semantics as a single and immediate instruction with the appropriate parameters that have already been compiled. Once we do that, we actually that line there basically chops off the last two previous items in the instruction stream, and then we append our new instruction in its place. And then there's the flag that says, yes, we actually did an optimization. Let's continue on with the next. So here's another one where we check to see if there's an OR immediate. If the value of the OR immediate is 0, odds are that is indistinguishable from a register to register transfer. And likewise, we check to see if we're doing an immediate and if these are the same destination registers, then we can collapse this into a single and immediate instruction, but with slightly different registers and with a consistent immediate value passed to the original and I. So these are some of the optimizations that you can work on. Here's a more sophisticated example in a third part here, but right now I've got defined about 10 individual cases that are written out like this. It looks like a lot, well, it actually is kind of a lot of code, but the fact that it's only 10 cases means that it allows it to be more or less pretty manageable. So the first example is an unsigned multiply, 32-bit by 32-bit, yielding a 64-bit value. And we do this the good old-fashioned way. We just keep counting. We just keep adding until we reach the end. Very simplistic. So when we look up here, one of the things that we see is this dupe if. This is one of the cases that I was telling you about earlier. And here we see it optimized out to a single branch equal instruction. Right? So if we were to do a dupe without any optimization, it first would allocate a register, fetch the item from memory, or I'm sorry, duplicate register X3 in this case, and then we would do a branch equal on that extra register. So here in this case, we actually collapse that instruction sequence into a single instruction. You'll note that there's a whole lot of stack manipulation here. We have to R and we have R from, and we've got an over here. But the core of what we're trying to do is we're trying to add two values, right? So likewise, what we're doing here on these three lines here, that all gets translated into two loads from memory because the top of stack is in X3, We don't have any other registers used at this point. And then we add them. Then we do a 1 minus and a recurse back. So there's our 1 minus. You'll note that, again, there's no stack manipulation here. It's all direct register to register operations. We subtract 1 from the top of stack, and then a recurse exit. Now recurse, because we do actually have state stored in registers, the compiler has to make sure that our in-memory image matches what the compiler thinks it should be. So what it's doing here is it's synchronizing, or committing, if you will, the changes that it's made to stack state back into memory. And then we jump back to the start of the loop. Now you'll notice some of these, I've notated here some lines that have a leak. What this is the compiler not being smart enough to realize that this register is actually dead. So even though we never make a change to the X6 register, it still stores it back to memory, even though that's a wasted operation. So while it does optimize out a significant number of stack operations, the more complex the stack operations, sometimes it gets a little confused and it ends up doing extraneous work as a result. Similarly, when we're actually done, we have this drop nip construct here. And this actually confused me for a while. I spent a significant portion of today's SVFig meeting trying to debug this, only to find out that this is actually working as intended. Because the drop nip construct should leave an item in the X3 register, which is the second item on the stack, but then it should drop everything around it. So it drops the top of stack and it drops the third top of stack around that. And that is a leak because we already have the value that we want in X3. This is a leak because we don't ever use this. But we do add the appropriate number of items to the data stack pointer, and then we return from our subroutine. So even though we have these false stack manipulations, if you will, which in this particular case totals 1, 2, 3, 4, 5, 6, a grand total of 6 cycles. Everything else is basically cycle accurate with at least my S16 X4 processor for the Kestrel 2. And then, of course, the actual act of pushing a 0 on the stack and then swapping and calling mul 0 produces this code here. You'll notice that it doesn't actually touch X3. It leaves X3 right where it's supposed to be. We just load the value 0 into X5, stuff it into the data stack, and then continue on our way. Here's a more sophisticated example where we're actually doing bit banging to produce the multiplication. And so here's an interesting case where we're actually checking to see if the low bit of the top of stack is set or not. And you'll notice that we actually collapse 3 instructions in this case. We're actually duplicating the top of stack, so that's 1 register allocation. We're loading the numeric constant 1, which is another register allocation, and then we calculate the logical AND, which reuses that. And so the peephole optimizer actually collapses the sequence of 3 instructions down to 1 because the operations allow that, and the register selections actually allow that as well. And once again, we have our collapsed state. But you'll notice here, this is kind of interesting because this whole 2/2R, 2 times R from, when you actually look at the code, there is a little bit of a leak, but except for the leaks, it's actually doing the correct operations on exactly the correct data items without a whole lot of stack permutation going on. Like you don't see, you know, explicit code for duplicating the stack or for swapping things or anything like that. And then you'll notice down here, I actually do Talcall optimization just like Machine Forth does. What I don't have implemented yet is, while I've got stack synchronization for the data stack implemented, I don't have it for return stack yet. So if I were to just execute this code as is, the X1 register, or which would be the return address that I pointed out above, that would be corrupted as soon as we execute more than 1 colon definition deep. But otherwise, this is actually correct instruction sequencing. And more germane to my purposes as a Kestrel developer, which has a bitmap display, if I want to plot a character on the screen, I do so by basically splitting 8 bytes to a bitmap. And this is some code to actually do that. And basically, the first thing I do is I check to see if, oh, that's actually a bug, but we'll go on from there. Basically, what we do is we actually set up a loop where we actually do this 8 times in a row, and for every time we do, we stop that. Let's get the right set of characters here. We actually copy one of the bytes, and then we advance the pointers by the appropriate items, and then we start over again. Well, if we actually look at this, we actually see, again, we're going to do a check to see if if our loop limit has been reached, and if so, we're going to clean up the stack, and we do that by reloading X3 from the appropriate item, and then we add our desired offset to the stack pointer, and then we return. If not, what we're going to do is we're going to grab our address, which is this over C# point here, and then check this out. We have a load and then a store immediately right next to each other, back to back. There's no intervening need to do any stack manipulations. There's no pointer fetches or anything like that. And that basically compiles the cfetch over cstore as a single operation. Conversely, we actually add our pointers directly to the registers, since the compiler knows exactly which items are in which stack items are in which registers. And then when we recurse, again, we have to synchronize what the compiler thinks the stack is with what is reality. And in this case, it's a leak because we never actually, well, actually, we do change X5 here. So that's actually not a leak. And then we jump back to our rows. Yes?
So when it processing these operations, the optimizer must know about things that it can safely inline for free, like over or not or swap, and other words which it should use calls for. Is that the case?
So the way the code generator works is it exports an interface that the compiler, quote unquote, is aware of. So these are all primitives. If you do want to call a word which is actually a subroutine, there's actually a call function that you can invoke, and that compiles a call.
So that's just primitives which can be optimized and then calls which are always.
Correct. Right. And that basically is the end of the examples. Now let me actually show what some of this stuff looks like. So this is actually kind of getting to what you were talking about. These are all, so right now everything is written in Python. It's about 600 lines of Python code. And like I said, this is all just a hack day type thing for me. So this is all just a toy implementation. But the idea is we define the existence of a subroutine here, and then I encode as Python calls every single fourth word that a compiler would actually see. And I call them in the order that they're intended to be called. The only thing that's extra is I have these extra optimize calls mixed in. And the o.commit call here, this is what actually synchronizes the state of the data stack against what the compiler thinks it should be, so that when we actually run this, it actually generates the appropriate code. And that is pretty much what I've been working on. And if you actually do a hypothetical at this point, because I don't actually have live hardware, but if you actually do a hypothetical cycle count of the code that it does generate, and you compare it against how much the equivalent code in the Kestrel 2 would take, which is a MISC architecture chip, they're actually cycle for cycle very competitive. They're not exactly equal, but they're close. And I'm actually pretty pleased with the initial results, especially when we actually take a look at the optimizer code. I mean, this may look really hairy, but it's basically all just pattern matching. So there's an if statement there, and the actual replacement is actually fairly small code. Right, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So about 15 actual cases. It's about 15 rules, if you will, that we can actually apply to the reducer or the optimizer, if you will, and it will produce code that's pretty convincing. Now, it's not exactly complete. If I were to use this to, say, target a more sophisticated fourth dialect, ANSI fourth, for example, we would need to add some more rules. Also, when I implement return stack support, I'm going to need to add some more rules for that as well, especially when I do subroutine calls back to back, because that's actually I wrote about this in a previous blog article, where doing that in a naive way is actually pretty inefficient. But that can be optimized out with the people optimizer as well. But yeah, generally speaking, it's actually pretty. It actually yields pretty good code. Any questions? When I actually have a working, usable system in software. So what I have right now, if I do, yes. So I'm in the developer. I'm actually in the Kestrel thing now. So if I do, well, let me just make sure I'm all up to date. So right now I have it printing out a header, the machine language monitor, that thing there. And now if I just type in a bunch of words, it prints them all out on the screen. That's basically where I'm at. I think once I get something where I can actually load data from an SD card, store data to an SD card, be able to plug in programs or be able to execute programs from a machine language monitor. Basically, once I get it to a point where it's an Apple I, a 64-bit Apple I, I may consider at that point going live hardware. Cool. Well, thank you.
Sure, I will say something to wrap it up. I'll say thanks for the mic. Well, I'd like to convey my applause and thanks to the speakers today. And thank you on the web, and thank you, those of you that are here physically, for joining us today. And we'll hope to see you next month. In May, we will be having excursion to the Maker Faire in lieu of our monthly meeting. So go to the Maker Faire or don't, but don't come here. We won't be here. Thank you very much.